I'm Tista, and I will talk about archival studies for now, from shifting the focus from real-time follow-ups, which we have been hearing since the beginning of this morning. And I will talk about following up sub-threshold gravitational wave events with sub-TeV neutrinos, which we are detecting, which IceCube basically detects. And yeah, so I will take the liberty to not reintroduce you to IceCube because I think Massimiliano already talked about that in his talk. I would just briefly mention the main motivation before going to the details of this analysis, that we basically are trying to contribute to many ongoing efforts in finding out a common source of gravitational wave and neutrinos, which we are yet to find out to basically complete the multi-messenger picture, which, I have mentioned here to basically complete to find out the missing piece of this puzzle. And to do that, we of course need information about neutrinos and gravitational wave events. So for the neutrino events, I am using the Greco dataset, which is available within IceCube. It's not yet publicly available. And it is an all-flavor dataset which covers the energy range of the order of 10 to hundreds of GeVs. And it has already been used for different transient follow-ups as a complementary data set to the GFU version, which also Massimiliano talked about in his presentation. We have used that for searching for neutrinos from novae and also to follow up the boat event. We're also talking about that yesterday, and it was also, of course, used for gravitational wave follow-ups. And now about the gravitational wave events, we all know that there are 90 confident events, which the LIGO-Virgo and Kagra collaboration has provided. Basically, they have detected and provided us the information about these confident events in the 3 transient catalogs, which covers the event information from the past 3 observational runs. And these are mostly the CBC candidates, which were identified by the template-based search and search pipelines, which are noted down here. And for all of these, the 90 candidates, they were followed up by IceCube previously. And for these candidates, the threshold criteria, which is defined by the LVK collaboration, is that the false alarm rate should be less than 2 per year. And specifically for the transient catalog 3, they also mentioned that the confident events should have a p-astro, which is greater than 0.5. However, for the candidates which were detected during the 3rd observational run and which are covered in the transient catalog 2.1 and 3, we also get information about the sub-threshold gravitational wave candidates. So we have almost like thousands of these candidates which have a false alarm rate, which is not as low as 2 per year, but it is significantly low, which I have mentioned here, which is like less than 2 per day. Now, these candidates were also identified by the template-based search pipelines, but they were not followed up in real time because we only got the information after the release of the transient catalog. So that is the goal, the primary goal of my work so far, that we want to follow up these candidates and do archival studies to basically find out the neutrino counterparts, which lie in the energy range of basically 10 to hundreds of GeVs. And the next question that will very naturally arise Why? And why do we basically want to, why do we care about these subthreshold candidates? The obvious answer is we don't want to miss out on any information, any interesting information which these candidates can provide us, these sub-threshold candidates can provide us. And whatever the outcome of this analysis, we will, of course, gain some interesting insight. And it will, of course, improve our understanding about the current threshold of gravitational wave detection, which will not only beneficial for like setting up future real-time campaigns, but it will also help. The knowledge will, of course, help the future detectors as well. Sorry. So to do that, of course, we first need a set of sub-threshold candidates. I basically try to find that out by looking into the candidate lists that we have in the transient catalog 2.1 and 3. And the first step was to, of course, eliminate the candidates which have a false alarm rate less than 2 per year, because those are the confident events which have already been followed up. And then I try to find out the candidates which have a false alarm rate of less than 2 per day, which corresponds to the approximately to 730 per year. And these candidates are shown here in this dotted region for both transient catalog 2.1 and 3. Now, the next step was to look into the pay-astro distribution of these candidates, because it's the natural question, like how probable are these candidates? How likely are they to being originated from an astrophysical source? And it was found out that in most of the cases, the candidates have pretty low p-astro value, which is close to like 0, which is very less, like less than 0.1. And that's why we say that, that's why we decided that for now, we will only look into the candidates which have a p-astro value greater than or equal to 0.1. And this is the distribution we have from the transient catalog 2.1 and 3. And in total, we have 90 CBC candidates from these two catalogs with p-astro value greater than 0.1. And among those candidates, we have 16 NSBH, like probable NSBH event, which were all detected by the PI-CBC pipeline. And in case you're interested, I wanted to show the localization of these candidates. It is not great. In some cases, you can see that even the 50% containment, like area containment from the sky map could be pretty high. But of course, we can improve this if we are able to find out neutrino counterparts, so to say. So that also serves as another motivation for us. Okay, so before getting into the next part, I would like to reiterate the fact that we are now trying to follow up the 90 CBC candidates we found out within the false alarm rate threshold, which has been defined by the LVK collaboration, and we have chosen the candidates which are lying within this p-astro range, which is like between 0.1 and 0.5, and we will look for the sub-TeV neutrino counterparts, which will be coincident spatially with these candidates within 1,000-second time window. Now, to do the follow-up, of course, we are following the unbent maximum likelihood method, for which, of course, we need a likelihood function. And this is the likelihood function which we are using for this analysis, and it was also used for the following up of the confident events, confident gravitational wave events before. So here we have basically two parts. The first term is taking care of the transient nature of the gravitational wave source, and the second this part basically contains signal and background terms, where NS is the number of signal neutrinos, NB is the number of background neutrinos. SI and BI are basically the probability distribution, the signal and the background probability distribution. And yeah, now to maximize this likelihood, we can also maximize a test statistic, which is another quantity which we are defining using this likelihood function in this way, which is basically a ratio of the likelihood function which has some signal term in it to the likelihood function, which is the background like. And on top of that, we have included a spatial triad term to take care of the extended nature of the gravitational wave source, because of course it is not point, like it has a large error, like a localization, like sky coverage. So we want to scan through all that region. That's why we have this, oops. Anyway, so we have this omega k term, and now we can decompose this test statistic into two parts, which basically looks like this. The first part is the standard point source TS, and the second part is the spatial penalty term, which will be 0 for the best fit gravitational wave location. Otherwise, it will be increasingly negative in less probable regions, so to say. Now, to see how this framework is working, basically how it's behaving, as I have not yet unblinded the data, so to say, we are using a blind data set we can take an example case of a subthreshold candidate, which was detected by this GST LAL pipeline in the first half of the third observation run, which is like in 2019 in July. And it looks like this. It has a P astro value of 0.35. So what we can do basically for these, for a candidate like this, our first approach will be to generate a background like TS distribution. And to do that, we are basically scrambling the data set for 10,000 times to basically generate 10,000 independent trials. And out of which we have a distribution which will look like this, which is looking like this in this case, where we have a median line of the distribution, which is coinciding with 0. And we have also identified the 3 sigma deviation. These two are very important, like two very important quantities to basically identify the 90% sensitivity and the 3 sigma discovery potential flux. Now, what we can do for the next part is we can start injecting signal-like events on this background-like distribution. And our goal will be to basically move the median of the TS distribution towards the 3 sigma deviation. So we are basically injecting signal neutrinos on top of this background-like distribution and trying to find out trying to find out the neutrino flux, for which we will have a TS value, which will be greater than the median line in the very beginning for 90% of the cases, which will give us this 0.9 passing fraction. And corresponding to that, in this case, we have a time integrated flux, which is also energy scaled, and it's in this case, it's less than 1 GeV per centimeter squared. And then we can basically do the similar thing for all the candidates, which we have found out, the 90 candidates I was talking about. And I have not included the plot in the main presentation, but it was mostly found out that this 90% sensitivity flux tends to be lower. So the sensitivity tends to be better for the gravitational wave candidates, which are located, which have a part of its sky map located in the northern hemisphere, compared to that when the sky map is located in the southern hemisphere, which is not also a very new feature. We have already found that out for other IceCube dataset as well, in other analysis as well with IceCube dataset. So this is what we are currently doing. We have completed the sensitivity studies with the candidates we have found out from the Transient Catalog 2.1 and the work with Transient Catalog 3, like the subthreshold candidates from Transient Catalog 3 is almost done, but it's still not there. After we finalize these studies, we will request for unblinding, and then we can basically quote the result. And of course, eventually the goal is to also move this analysis to real time, because we are also now receiving the subthreshold event information from LVK. So why not follow those in real time using IceCube data, like different data sets? So yeah, that is the ultimate goal for now. So thank you for your attention.